And just to start out, I've had a bit of an issue with my voice today, so I hope it lasts the 40 minutes. But to break that up, I'm happy to take questions during the talk, and we'll try to go to the end of the talk and use all the time. But so there might not be a lot of time at the end. So please do jump in. And just to start, what being a director of the file and storage team at Red Hat means that is if you've ever lost your data on a Red Hat box, it's probably my fault. Yeah. So what we're going to do is talk in general a little bit about what motivates storage hardware and go into more detail through the talk about how file system and storage adapt to that, and give you a lot of detail about two kind of conflicting types of storage: persistent memory and scheduled magnetic drives, or SMR drives. Anybody ever heard of either of those? Matthew, you don't count. John, you don't count either. And neither do you, Dave. Yeah, so one of the things that makes life hard for file system people is we don't write a file system for each specific workload. Pretty much we're supposed to be general purpose and let any crazy user run anything they want on what we give you. Historically, the job was pretty much make it go as fast as possible, measured as bandwidth. You know, how many megabytes or gigabytes a second can you drive through your box with a big high-end disk array behind it? We didn't have to worry about radically different storage types. And very specifically, you know, we all knew storage was really, really, really slow, right? So most of you using your laptops don't actually write to the disk very often. So if I put the fastest storage in the world, you wouldn't run, you know, Firefox any faster, or even Chromium. You know, it depends. But you know, the tensions of making things faster, more complicated versus easy to use is another thing that I've done different talks on. In Linux, we've made life complicated a lot of times. So again, we try to make it easy to use out of the box without having to tune and twiddle and turn knobs. It can lead to a bit of complexity, though. This is not a diagram I put together. This is a great one you can find if you just Google the title. A fellow in Germany put this together. This is kind of a high-level overview of the Linux I/O stack. And you can imagine that's a lot of complexity. And the faster we go, the more you transition through these modules of code, you know, the more we induce latency. It's okay if at the very bottom, the thing you're talking to is really high bandwidth but really slow to talk to. It's not okay if the thing underneath that all is really, really fast. Anybody here have a Fusion I/O drive or Micron card or any of those? You've started to see, even with that class of parts, that you don't go necessarily as fast as you could go, right? So, going faster. As I said, you know, historically, we were always talking about bandwidth. You know, backup bandwidth is gigabytes a second. Really big storage servers, big servers with really high-end storage can do gigabytes a second as well. But, you know, we weren't really talking about millions or 10 million IOs per second, with rare exceptions. The focus on latency and storage was just never there, right? So if you think about, you know, our siblings in the networking stack, they're driving over gigabit and 10 gigabit and 40 gigabit networks, lots and lots of packets. We've never tuned the I/O stack and file systems to do that yet. Now, we can do better, right? So the first thing that happened, you know, kind of in the SSD space is we got SSD devices that were SATA or SAS form factor, not to mention those yucky USB sticks, which I'm not going to talk about at all because they're barely really storage. But they looked like real disk, right? You wrote to them a whole block at a time. You could write just about as fast, maybe a little faster. The bandwidth wasn't great, really, with that class of drives. But the thing that made them different was random reads were really, really fast because you weren't moving those big rotating heads. I mean, that's what causes disk to go slow, is if you're not doing concurrent reads or writes, you're thrashing mechanical arms back and forth. And that takes a lot of time. You know, but, you know, everyone came to us at that time, I don't know, 5, 10 years ago, and said, this means you have to rewrite the entire I/O stack. You know, file systems as we know it are done. Well, we actually coped with these pretty well, right? And most of us put SSD devices in our laptops, our servers. Life didn't really change. We had to tune some things, but it did do traditional block-based I/O. They were real drives, and we could pretty much keep up with them. When we got into the new class of PCI Express cards, the things that plug in, they still emulate disk, but they bypass the whole SCSI stack typically. Typically, they bypass SATA. Some of them emulated HCI, I think, but those are kind of rare, few and far between. But the thing that the hardware vendors did here is they put a lot of DRAM in the cards. So you're effectively writing almost to DRAM a lot of the time with big batteries or some other mechanism to make it look like a drive. What happened is, with this first class of device, you spent $10,000 on this card, and we could give you maybe 10% of the IOPS, or 20. It took us a while to catch up to where you're getting reasonable value out of your investment in the storage. And again, that wasn't really accidental. I mean, it was almost intentional. We'd always assumed in the coding of the I/O stack that you want to do everything you can to avoid touching that device. Coalesce things before you send it down. It was always better to wait and see if more things were going to come down and join you before you talk to storage than just fire it off. Well, even with this class of device, that kind of algorithm was wrong. So again, these devices pushed us beyond where we were happy to go. I think we see, I don't know, Matthew would probably know better, a few 100,000 IOs per second with PCI Express cards today, 500,000 maybe. People can go a little bit faster than that. And that's not too bad. Anybody here need more than 500,000 IOPS out of one card? Dave? Yes, yeah. You can complain. Yeah. So again, most of the time we're not actually I/O bound, but there are things that do need a lot of low latency, high IOP transactions. And you can think about it as even just hosting a ton of virtual machines on one big, gigantic server where they're all doing non-coordinate I/O. That wouldn't work well on rotating drives. With these very high-speed SSDs, it would be kind of workload you could do. So, was there a question? So, some of the things that we were going to do is, first of all, look at the obvious things. Where are we stuck in the stack? Why are we slow? And one of the first things that popped out, Jens Axpo started looking at how to get away from having a single queue to go down the I/O stack. In the 13 kernel, he actually got his multi-queue block layer in. The other thing we looked at is the I/O scheduler, right? Traditionally, we would plug the scheduler, let I/Os coalesce, let us think a bit, hope that more would come down, and then fire it off. You can see that that's not a good idea if the time that you think is longer than it takes by, say, an order of magnitude than it would to actually finish the work. That's kind of like your teenage kids, right? You put it off, put it off, put it off. Sometimes it's just faster to do it than to think about it. Looking at tuning the I/O stack to just like you would for interrupts and other things, to be aware of SMP and NUMA architectures. And of course, just kind of analyzing the whole stack for lock contention. Now, some of the things that people did in this time is they put device drivers above the whole stack, right? So if you look at a Fusion I/O card, some of the other proprietary drivers, the driver actually skips the whole SCSI stack, SATA stack, a large part of the whole I/O stack, in fact. That's great for reducing latency and making it go a little faster. It's really horrible if you have to recode at that special device driver layer all the stuff you just took out, right? So there are things we do down there that are important, and it's good to be able to make it better as opposed to avoid it and recode it in part. So that was going faster in terms of IOPS. How about bigger? Anybody here ever run out of storage? Yeah. Yeah, so in my mind, big is a lot bigger than in most people's minds. Anybody here use 16 terabytes in a single file system? Only 3? Oh, a few. Dave, you'd better. That's what we pay you for, Dave. Yeah. Yeah, so today, traditionally, even most high-end enterprise users are more than happy with a handful of terabytes per file system. If you get into video recording, a lot of high-end scientific applications, you can get to 100 terabytes. We've had some customers ask us at Red Hat for 500 terabytes for a petabyte file system. And the truth is, 16 terabytes, which is all most people ever thought about using for many, many years in Linux, is not that much. I mean, a single drive expansion shelf can have like 10 plus 2 drives. Those drives are 4 to 6 terabytes today that you can buy. You're 40 terabytes without even blinking. And not to mention you can cascade multiple shelves behind one server. It's all pretty cheap. So you can get 100 terabytes pretty much in your basement if you have, I don't know, 10,000 bucks, maybe a little less. So it's getting a lot denser, a lot bigger, and we have to continually look at how these technologies push us to go bigger. It's not always big, and that's kind of in conflict with the low latency stuff. There are downsides, and I won't dwell on this too much, but as you have a larger file system, the best thing is you don't have to worry about allocating space between multiple buckets as an application or as a person. You can put all your video recordings in the same file system, not have to spread them apart and not have to figure out where you left that. It can have better performance because we know about the file system itself does optimizations for seeking the heads and allocation. And it can prevent, when you carve up a RAID stripe, even if you have an enterprise array, those heads still move in the drives internally. So sharing a RAIDed LUN on an external storage array actually often is slower than having distinct LUNs that don't have physically shared drives, right? It's not always true that you can put a lot of non-volatile memory in a big array, but you can be faster just having fewer bigger things than lots of small things with shared physical resources. There's also bad things. Anybody here ever wait for FSCK for more than like an hour? Yeah, right? So backup and restore. If you ever want to back up your data, if you have a petabyte of data, you need a really big tape archive or another big petabyte file system and a really big fat pipe to copy it over to. File system repair traditionally scales not so much with file system size as with the complexity of the amount of metadata and things, but it takes a long time to repair a file system. And you could potentially have updates on a single journal with a giant file system. A lot of people work around it. I mean, we work hard to put a lot of stuff into a journal transaction, but there are things that could bottleneck. One important thing with really large storage is you also have to have sometimes really large servers. How big was the server, Dave? When you had the petabyte XFS file system, you needed a terabyte of RAM?
It was prepared on a 2 terabyte machine. It was only 600 terabyte file system.
Yeah, so a 600 terabyte XFS instance required 2 terabytes of DRAM to run the XFS repair program. So your file system was great, but actually,
It took 2.5 hours to run.
and it finished in 2.5 hours. So it was fast once you had the DRAM. Without the DRAM, it would probably run really slowly and page a lot for like weeks. Yeah. Yeah, so this is things people don't think about. So big does come at a cost. And we have worked, by the way, to make sure you don't need that much memory now. And the metadata itself, I mean, as you have these really huge file systems, if you have lots of files, the objects themselves take up a lot of room. So we have to be careful about how big we let the objects that we accumulate be. So this is actually getting into the more interesting part of the talk, I hope. Anybody ever hear about persistent memory? All the way back, like in the 50s, right? Core memory, right? If you turned off your computer, turned it back on again, that program would crash right away, right? All the bugs were still there, right? You hadn't cleaned up any of the state that you left. Reboot your box. If you ask a sysadmin, does it work after you turn it on and off again? Core memory, that's not a good answer, right? So persistent memory, this is kind of back to the future in some ways. But there are parts now that have a few unique characteristics. One is that they look kind of like DRAM. You can buy parts now that fit in DIMM slots. They have various ways of persisting the memory. The ones that I know about, for example, snoop for power loss on the motherboard. They have supercaps or batteries and destage to flash. But as long as it's up and operational, you're effectively writing to these persistent memory parts at DRAM speeds. There are a bunch of new technologies coming from a bunch of different hardware vendors, and I'm not going to talk about any of those. You'd have to go talk to your hardware partners specifically about those. But the really critical thing that makes them different is, A, they're byte addressable, B, they do persist over a power outage. So I think it's kind of neat to have these coming. It would be really even better if we didn't have hundreds of different device drivers per vendor, or per instance. So we're looking at how to deal with these. And kind of at a high level, you think of these parts like DRAM, they're not going to be gigantic. It's not necessarily going to be a terabyte DIMM, but think of them as being the same cost and performance and capacity as a DRAM is today. Hopefully we'll have a pleasant upside there. It implies that if you had a box with only persistent memory technology in it, it would probably be pretty expensive. It's not that you won't have some of these, maybe in smaller systems or as cost comes down over time. But I think this means that we're going to have to look at ways of combining these parts with traditional rotating storage as well, right? So I think it'll be rare to have pure persistent memory boxes. You'll probably have both. Also like DRAM, these parts might do 1 million IOs per second per DIMM slot. If you have a lot of DIMM slots, like 16 or 32 DIMM slots in a big server, your performance expectations might be that you don't want the IO stack to be the bottleneck there. You'd rather it be the CPU. So we have to make sure the IO path scales up to linearly with the number of parts. So this is back to that same old question. So as people talk about persistent memory, the first thing people say is, well, clearly you can't use the same file system and the same IO stack anymore. There is good reason for having the stack we have today. Anybody here a file system developer aside from these guys that guy over there? One of the things that makes file systems sane and survivable over power failures is we have a state that's active as you're running a box. And we have a state on your permanent storage that's always consistent. You can pull the cable between the box at any time. We promise, we try. And you should be able to remount that file system and just go. Now, there are bugs occasionally, or there are hardware errors that will break this promise. But the transition from what's in DRAM and in your page cache down to what's in the permanent storage is very carefully orchestrated through block-oriented updates through journals, or like Btrfs will do pointer twiddling, things like that. This is a real fundamental underpinning, and it's not something you'll get away with just because you have new technology. Persistent memory could collapse those kind of two states, right? If your DRAM was only persistent memory, you could imagine getting away from this, but you still need to figure out mechanisms to do some kind of transaction between kind of the working state and the persistent durable state that's crash recoverable. And my favorite note as a file system person is fsync is still needed with persistent memory, right? If you're playing in DRAM, you have these nasty things called CPU caches. So your fsync has to go through and flush the data out all the way to the persistence domain on the part, right? So you still have to do odd things like that. There's a Storage Networking Industry Association group based I think in Colorado or somewhere. It's driven by the storage industry. And they're working on a programming model to try to figure out how to make a programming model more than a standard set of APIs that allow us to think about how to program these parts. So draft out there, I have a pointer to their website here. You can have a read of that if you're really into storage. But high level, I have the opinion that most application people never like to use new APIs or new system calls. And so I'm a little leery about anything that would actually be seen. The kind of takeaway from the persistent memory point of view is these parts want to have almost no code between the application and the storage, right? The big push is to get out of the common I/O path all the code out of the way, right? You can do this in a few ways. Say mmap the code to execute in place. I think Matthew will be talking about this tomorrow at the same time, same room, I think, at a much lower level of detail than I am. But more or less, this is one tension. Get code out of the path. Now, here's the trick. The same year, same time we're looking at this kind of stuff, we have new devices coming in that have almost exactly the opposite requirement. Shingled magnetic recording drives are a new type of really high-density drive. If you think about how drives look almost like an old phonograph, right? They have these grooves, and they have a little head that writes or reads. They've gotten so fine-grained that you can't actually, with these new drives, overwrite just a single track anymore. You have to overwrite a big chunk. There's a lot of detail here in these slides. You're welcome to peruse them at more length. But when you write, you're going to destroy potentially parts of tracks. And very specifically, what that means is they're going to have really odd characteristics in terms of performance. Specifically, they're going to be really good for throughput. They're going to have really horrifically bad latencies. Right, so it's the polar opposite of our stuff. It's kind of neat, and I will point this out, that the drive industry came to the Linux storage developers first before they came to any other operating system vendor to try to solicit our input on these parts. The way these drives work in a kind of finer grained detail level is you chunk them up into bands. Each of those bands can only be written sequentially with writes. Reads can still be random, But if you start writing to band 0, you have to write sector 1, sector 2, sector 3, sector 4. If you seek backwards, that's a violation of their operating model. A little bit more detail. So when the drive vendors first came to us 2 or 3 years ago, they said, well, you know, if we put a lot of money and hardware into these drives, we can hide it all from you. And every single person in the room raised their hand and said, hide it. I don't want to have to deal with it. Yeah. This is very much like what the flash-based people did. If you think about the PCI Express cards and SSD cards, they have a flash translation layer. These drives need the exact same kind of technology. They have effectively a lot of weird restrictions that are internal to their internal mechanisms. It's great for us to ignore it, right?
But can you trust them?
How can you trust them? Well, actually, to a point, and this was announced publicly, Seagate's shipped millions of these drives already. So you have these things called SMR, drive-managed implementations of SMR in the market today. You probably don't know about it. What you'll have is really weird performance anomalies, because if you drive a random workload against it, the firmware has to match up stuff, and we have no awareness of it. This is okay. It makes it really easy to use. It makes it easy for the drive vendor not to have to worry about not being able to sell into certain markets or consumer boxes, like video recorders, for example, are good with this stuff, because they're usually pretty sequential anyway. But it's not. It means they have more cost, and that means we have more cost.
Rick?
Yeah.
I just want to make a point to the person who asked, how do we know we can trust them? Even for a regular drive today, if you talk to a drive firmware engineer from someone like Seagate or Western Digital, they have thousands, tens of thousands of lines of code already running in these drives.
Yes. Oh, you mean how do you trust it? So he's saying that there's tens of thousands of lives in all these drives. In fact, there are rumors of people putting entire Linux kernels down in the little daughter cards. Yeah. You know you can't trust those Linux guys. Yeah.
We know we don't trust the FTL on most SSD already.
Yeah. I think, well, there's two answers. I mean, the issue of trust is two-level, right? If you're talking about drive vendor people hacking, like NSA hacking, that's one thing, which I don't think is so interesting. But just badly implemented drives, it happens all the time, right? And the big storage vendors, I worked at EMC for 10 years building storage arrays. You take these drives for 3 to 6 month burn-in periods, you pound the tar out of them, and you know, at the end of that, you've worked out most of the bugs. I will note that the drive vendors will often ship earlier than the storage vendors' qualification cycles are. So if you get the newest, shiniest, highest capacity drive in the block before you've seen it shipped by like NetApp and EMC and IBM and HP, you're probably taking your chances. You're helping them do QA, which we deeply appreciate. Yeah. Yeah. So again, you know, the SMR drive managed disk, hide it all from us. This is great. Life is easy, right? We don't have to change anything. You don't change your app. You don't change your kernel. But what if we just tell you about the weirdness? What if we let the kernel discover there really are these bands? You know, we'd like you to do these appending-only writes per band, and these could be like thousands of bands per drive. And if you get it wrong, we'll forgive you. We'll put just enough hardware and buffering in there to make it look like it almost really worked, and you'll have some performance anomaly only then. This is kind of in between, right? And it lets them cut some cost out of the drive, but it means we can mostly ignore it, right? You could run any existing file system on it without touching it or tuning it. This is kind of boring, right? I don't know. It's kind of nice. We could do some things with it, but you can. It's not really a hard problem, right? The third model that they're talking about, and this is what everybody was actually mostly interested in, was SMR restricted drives. And this one, if you do a non-sequential I/O to a band, it'll reject the I/O, so you get an I/O fault. Things like your BIOS might not boot, right? I mean, you know, this will be the hardcore model. The reason you want to go to here is it actually lets you move a lot of cost out of the device, which again we pay. And when you talk about thousands of drives in a big storage array, you're paying that cost per drive as opposed to aggregating the cost in a server. And if you didn't realize this, most storage arrays these days are run with Linux as the kind of internal storage platform. Not 100%, but quite a few of them. So I'd like to see if we can get there. It does put a lot of complexity back in our stack. which means the exact opposite of what I said. They want us to put more code in the I/O path, right? So this is the kind of tension we deal with all the time. The persistent memory people want us to get code out. SMR people want us to put code back in. And you can clearly do both at once, depending on the case, but it's interesting to do this. So I'm going to talk a little bit about stuff just at a high level that we're doing. Yep, go ahead.
So you envision dealing with the SMR on the I/O path through some fancy block layers thing, or rather having a dedicated file system, like a log-based file system that would naturally do things in the way that is programmed?
Yeah, there's some slides on that in a bit, so I'll get back to that. Okay, so the question was, where should we deal with it? Right, and the short answer is we don't know, but I'll show you what we're kind of thinking about. Yeah, so the neat thing is, and this is just kind of a shout out to Matthew again, this isn't really persistent memory related, but one of the banes of my existence as a Linux distro person is having binary drivers in my customers' boxes, because we can't help you when they break. With PCI Express SSD cards, we hope to see the end of that popular trend when things like NVMe Express, which Mr. Wilcox has kindly worked on for years, there's a SCSI over PCIe driver. These will both be open source drivers. They'll let us have out-of-the-box support for PCI Express cards. That'll be great, and I think we'll actually sustain most of the IOPS we need for those class of parts. And again, I probably don't have to say to this crowd, but we really like open source drivers. So, and it means that even the vendor and end users can change the kernel and test with new stuff. You can't do that when you have proprietary drivers. Going back to my assumptions, and I'll start again, Ben, I'll get to your question about SMR in just a second. But my assumptions about how we have to deal with persistent memory start from the fact that I assume applications will never change, right? How many people here write application code? How many of you have ever used fsync incorrectly? Yeah. Too much? Too little? Not at all? Yeah. You know, how many people use ODirect IO in their application? Maybe about half the people. Async IO and ODirect? Okay. Yeah. Fadvise, right? As we add more complexity, application people are less and less and less likely to ever use it, right? So I fully realize that we'll need to have special cases and special support and maybe special tunings for the most demanding applications, but 99.9% of us will be using applications that won't be tuned to any new APIs that you ever put out, right? We just have to live with the existing read-write file system path with names and everything. And as I mentioned earlier, a lot of times it doesn't matter, right? If an application is not I/O bound, if it's really CPU bound or waiting on the web to respond to you, who cares how fast your storage is if you have to wait 10 years? So I think the first approach we're going to take as a community is seeing if we can make these persistent memory class of parts just work out of the box with the existing stack. So if you love ButterFS or XFS or ext4 or whatever, go for it. We'll hide it underneath the device driver in a new device driver for you. We'll try to make the whole stack as fast and low latency as possible. And hopefully, we'll move the I/O, the bottlenecks away from the file system and I/O stack to somewhere else. Probably your CPU if we're lucky, right? You never get rid of bottlenecks. You just kind of shift them around to make it somebody else's problem. So that's our goal, is not to be the villain. The first foundational thing we need to do here is make these really cool byte addressable parts look like a boring old disk again. Right, and there's a couple of drivers that have been proposed, one from Intel Research Labs that was kind of really prototype level, I think. There's another prototype coming out of Red Hat. Jeff Moyer has a driver in the works. And again, you'll potentially be double buffering your data. You might have regular DRAM and persistent memory and do transitions in some of the allocation paths of a file system. But there are ways to avoid it if you're using mmap or other things or execute in place code. We can shortcut that path, right? So it's kind of doing, I hope, for the performance path, getting you the performance you need. For the boring old bookkeeping of file systems, we'll probably use more of the traditional block path. I think, are you talking about XIP tomorrow?
Yes, I am.
Okay, so I will let Matthew talk more about that. But XIP is something that's been hotly debated. If you missed the cage match between Dave Chinner and Matthew earlier this week on Tuesday, I think they both emerged standing.
You can still run faster.
Yeah, Matthew outran Dave. Yeah. So again, Matthew will be speaking about this in this room, this hour, tomorrow. Jens Axbo, his multi-queue block driver is in the upstream kernel today as of 3.13, I believe. It doesn't have any consumers yet. I think your NVMe driver is being adapted. Is that true?
The NVMe driver, someone's posted patches for the NVMe driver. There are problems there. Those patches are not going to be accepted today.
I have to repeat everything you say.
Yeah.
Yeah, so the NVMe driver has patches to opt in. You have to opt into the stack, right? So VirtIO is opted in, so we'll start getting some users. Yes, and if you're a lucky RHEL 7 beta user, we pushed aggressively to put the multi-queue stuff into RHEL 7 as well. Right, so because I do think it'll actually be a tremendously good performance enhancement for IO, for the IO stack in general, but it's going to take a while to get a lot of driver support. The good news is, if his original implementation sucks and has lots of bugs, you won't notice, because you probably won't be using it until we get the pain out of it. The other thing we have to do is just continually do the performance analysis of key applications that make a difference. There are certain things that we should tune more aggressively, especially like databases or maybe libraries, MySQL, things like that, where they actually do care to use these special APIs. We have to kind of pick and choose our battles and see how we can impact the entire ecosystem of applications and users in a really big way. Anybody who asks you to go fix all of user space, you're going to be waiting a long time. And I think that with all this tuning that we have in the works, we're hoping that XFS and ext4 will actually keep up at a fair clip here. And if you only get 10 million IOs per second instead of 12, I think most people would be pretty happy. And you probably won't be able to get there anyway with your CPU. So, getting back to how to bring these things together, if persistent memory is really, really fast and not that inexpensive, it's probably going to be likely that you're going to have both persistent memory and rotating storage or external storage for a long time to come. One of the obvious things that a lot of people have invested in the last couple of years is using block-level caches. So if you had a small amount, especially with the shipping technology of persistent memory parts, you could look at something like DM cache or the Bcache subsystem, store your block data on there, and your file system applications would do almost nothing. You could have very low memory, very expensive persistent memory client machines, and have your big, dense storage servers out, accessed over iSCSI or other remote protocols, NFS or some such. And of course, you could always export the persistent memory to an application. More sophisticated applications, say like a Ceph has an application or a Gluster. Sometimes you have an application which might be best suited to make caching decisions for you. Bcache I mentioned. DM cache is something that is a device mapper target that does caching the block level. FS cache is something that you can store with a file system cache on a separate block device for something like an NFS client or an AFS client. And there's a whole boatload of mostly proprietary vendor schemes that let you do block level caching with SSD devices. There are many, many ways we're kind of toying with using persistent memory parts. And again, there are a few who kept their hand up in the application space for all the weird APIs we have in the kernel. You. We'll be talking to you a lot, So again, the more aggressive you are in the need for speed and the more widely deployed your application is and the more IO bound it is, the more you're motivated to talk to us about how to use mmap, how do we extend msync or fsync or fadvise, all these things. Are the APIs we're proposing and going to be working on going to work for you? I don't expect this to actually impact a lot of people, but if we work with the right applications, it'll have a good impact on us more broadly. So, now back to, yep, go ahead.
Would rendering pipelines be one of the kinds of things that would do that?
Are rendering pipelines the right kind of application? I'm not that familiar with what the bottlenecks are with rendering pipelines. I would assume they're more CPU/GPU bound than they're disk bound. Because again, I think a lot of video stuff.
If you're talking about render walls for movies and that sort of thing, they are very disk intensive.
Okay.
Because of the size of the textures and the amount of data that's actually shifting around.
So
single frame might require a couple of hundred megabytes to a couple of gigabytes.
right. So a single frame could be. So you could have disk bound. So if you are disk bound, they could be faster. And I assume the bandwidth here, it's not just IOPS, these are actually memory bandwidth speeds as well.
It depends on the type of render being
Yeah.
done, whether it's seek bound or whether it's memory bandwidth or CPU bound.
Yeah. So it depends on the type of render. Yeah. So again, it always depends. Yeah. But so again, we're going to try to work first of all on getting things to work with the existing kernel. The cheapest and easiest way, Ben, to get this to work is look at something like Device Mapper. There's a DM-Thin target. It has an exception store, just like file system metadata, that tells you how to map blocks to, from a linear space to kind of a randomized space. Be perfect, right? But you still need an exception store space. So you need a look-aside device, like Device Mapper has anyway for a lot of things. So your exception store would have to be something which would allow random writes. You could tune the allocation from the main high capacity part to be serialized. There are special ways you could use file systems. Dave's talked about XFS's, what's the XFS video popular mode? The real-time JIRA mode.
There's a real-time device, which is a separate device with a deterministic allocator.
Yeah.
There's a couple of allocators that are designed for multi-stream concurrent file writes.
Yeah.
Making sure things don't get fragmented and so on, those sorts of workloads.
So tweak XFS, right? Again, have XFS have metadata on an existing boring device and have these high capacity stripes of drives externally. The storage vendors themselves have looked at a bunch of flash-based log structured file systems and have had some of the tape library stuff, strangely enough, that the tape libraries run out of the box on it.
I think that makes some sense. If we're using a setup where you're going to put your metadata in Flash and your actual large files for typically
Yeah.
for rendering movies, we're going to have huge files on SMR. So the file content that is accessible on the SMR device and the metadata is on Flash.
So you're suggesting putting your metadata on the flash and the large stuff on the disk. I like that model a lot. The people who are pushing SMR drives and don't sell flash are not as happy with it. Right? They'd like to sell you one device and it'd be theirs. I didn't go into a lot of detail about SMR, but there's also an optional way to have a couple of random write-enabled bands out of the 1,000 or 2,000 bands. So you could have a small, they were saying less than 1%. I said, well, maybe less than 10% would be useful. But it depends how much metadata we need. You could allocate part of the drive to have.
Something like SFS, they have the ability of having the metadata on one device and the data on the
Yeah.
other device.
That's what XFS does with the real-time device.
So the XFS real-time device, to repeat what Dave said, is it has the ability to have your metadata in one device and the data allocation in another. And we could do similar things with the ext4 potentially, with Big Alec or something, right? But you still need some metadata.
Not really.
Not as easily, not as cleanly, yeah. But I think, the push to have a whole new file system type invented just for this, I think is probably not a good short-term thing. I mean, by the time we're done in its production level, it might be ButterFS plus 5 years later, right? It takes a long time to get a file system stable. And this would give us host-aware things. The other path, by the way, that some of the vendors have done is simply look at putting it in a device driver. The device driver itself would need to have metadata, and it might have a lot of metadata, as the block space can be pretty large in these things. But, okay, well, that was basically what I had for today. So happy to talk more about this. So, any more questions? Please, yeah.
I guess coming from your original question about who runs big file systems and things, and I was confused how to answer that. The people who do big data now, more and more, aren't using a single traditional file system to encompass their big data. They're using things like Ceph, Swift, object
Right.
stores, right? So it's slightly different semantics required, much dumber, simpler semantics in order to go to those scales.
Yeah.
And the demands that are being placed on the actual block device and the file system between the cluster file system and the block device are much simpler. They're really just object stores now. They're just
Yeah, so the comment is, I'm going to summarize, is that a lot of the big data-like file systems, scale-out data file systems, use simple local file systems with smaller capacities. You might have petabytes and petabytes of big data in Ceph or Gluster or whatever, but the file systems locally are actually not as big or complicated. Well, the truth is that you still want big stores and you want to have reliability in those things. So
Well, what I was going to get to was things like, no, I don't. If I have to FSCK a drive, I'll throw it away and I'll reconstruct based on my radio trades from the other replicas.
Yeah, but you want cheap storage there.
Yes.
Yeah, it has to be cheap.
You recognise that you've piloted here and not things all and not that they're going to get in the way, but they're not things that actually are part of that anymore.
So I think, okay, so again, having some experience with this, I ran the Red Hat storage engineering group for the first year after we acquired Gluster. You do want, customers typically always want to get cheap storage, right, in their storage bricks. They also want performance, and they want low cost, right? You want all three, right? So having things big and locally big, there are some advantages, and having reliability in your system, even if you want to throw away drives, you say you want to throw away drives as opposed to repair them, but you don't want to do it very often because then you kick out rebalancing at the higher levels of the distributed file system, which can cause performance issues. So you want to have reliability at the storage bricks or storage servers as well. You want to reduce the downtime there locally, right? Which means more than you'd like. You still probably want to have cheap software RAID, which could use persistent memory and SMR drives, right? You want to make it reliable enough that you don't have to think about it, and when you throw it away, you don't need it back, right? But you don't want to do rebuilds and rebalancing especially in the cloud more than you have to. That would be my argument. It's a good talk for beer though. Yeah, and even if you don't care about, if you want to have it really high performance brick enablement for big cloud, you can still have high density drives with the persistent stuff caching, and still throw them away, right? And the caches, then you don't care. So again, unless you have the choice.
And some stuff we're seeing, you're down to the core primitives. You've got some workloads that are seek bound, right? And they're really, it's all about the number of signals and the seeks you can do. In which case, things like the persistent memory is a game changer. It's flash game changer. You know, only doing seeks to find directs.
Well, I will point out, so you're pointing out some of them will be very great workloads for persistent memory. But if you're talking about persistent memory even spread across multiple boxes at the scale of Hadoop or something, you're talking about giving some lucky hardware vendor a lot of money. Yeah, so it's big dollars, right? Okay, any more questions? Anybody want to work on SMR drives? I know that drive vendors are really desperately looking for some poor sucker. Yeah. Yeah. Okay, well, thank you very much.
Cool. Ric Wheeler, thank you very much.
Thank you.
Please accept this gift and this one more round of applause.
Thank you.